So we're now going through the rest of the paper. So question number 8, two identical steel balls P and Q are released from the same height h above horizontal ground as shown. P is released from rest, Q is projected with an initial horizontal velocity of 5 meters per second. Air resistance is negligible. Explain why P and Q hit the ground at the same time. So both are the same height above the ground, and when we talk about hitting the ground, because this is a vertical variable, we must look at the vertical aspect of things. So I think it's pretty obvious that neither of these have any vertical velocity. So because initial vertical velocity is 0 for both of them, and the acceleration due to gravity is the same for both of them, so the time is also the same. In analyzing this, I have used the first equation of motion, right? So time would be equal to v minus u over a, right? So for them to hit the ground at the same time, so initial velocity is 0 for both of them, and a is 0 for both of them as well. Sorry, a is not 0, a is the same for both of them as well. So I'll say that initial vertical velocity, or I should say vertical component of velocity, is 0 for both, and vertical acceleration, which is basically acceleration due to gravity, is same for both. Next part, P hits the ground with the speed of 4.2 meters per second. Calculate h. So P is the one which is just released. So I know u is 0. I know I need to find h. I know acceleration due to gravity. Speed is given, and I need to find h. So u is 0, right? V I know is 4.2. S is basically h, which I want to find out here, and acceleration is acceleration due to gravity, which is 9.81. So I know that downwards it's going to strike, so I am using the sign convention that downwards is positive. So acceleration is also 9.81. That's also positive because that's also downwards. So the equation of motion we would use is v square equals u square plus 2as. So s is going to be v square minus u square over 2a. So v is 4.2 squared. There's no u here. Divide by 2 into 9.81. So that's going to be my answer here. So if I do this, 4.2 squared over twice of 9.81. This is 0.8999, so 0.90 meters. Q hits the ground with a speed v and an angle theta to the vertical. Determine using a scale diagram v and theta. All right. So we need to find v and theta. So for this, we'll need to make the triangle. So for this, let's see how this one would be done. So I know that for this one, whatever is the vertical speed, which is 4.2 here, is also going to be the vertical for this. So that's going to be 4.2 downwards. And because this is a case of projectile motion, so I know that the horizontal is going to stay the same throughout. Why is that? Because there's no horizontal force, so there's no horizontal acceleration. So then this is supposed to be 5. For this question, because it says use a scale diagram, so you need to define a scale. So for the scale, I think one which is very obvious is this, that if you take 1 centimeter to represent 1 meter per second, that's your scale. So you draw a 4.2 centimeter line, you draw a 5 centimeter line. To make head to tail rule work out, you can superpose this in this way, and this is basically the resultant, which is what you're looking for, right? And the angle with the vertical would be this, which is theta, and this is also basically equal to this. So once you make the scale diagram, you will just measure this or you can measure this and this would be theta, and you'd measure the length of this line according to your scale, it would be the answer, right? If it was not a scale drawing question, then it's also really easy because it's just Pythagoras. So the answer should be, because I don't have a scale to use here, so let me just do this anyway. So 5 square plus 4.2 square under the root, which turns out to be 6.52. And similarly in this case, when you have to do theta, so theta you can then find using trigonometry. So you can use tan equals opposite over adjacent, right? This is opposite. So tan inverse opposite, which is 5 over adjacent, which is 4.2. And this turns out to be 49.96. So this is basically 50 degrees, right? This is theoretically what the answer should be. The procedure is repeated using plastic balls R and S. R and S are identical to each other, have a greater diameter than P and Q, have a smaller mass than P and Q. So a greater diameter basically means a greater volume, but despite the greater volume, they have a smaller mass. Explain any difference between the time taken for steel ball P and plastic ball R to reach the ground. So plastic ball R and steel ball P. So the ones which are both just dropped. So they're not projected, they're just dropped. So which one is going to be, so how is the time going to be different? So obviously I know that if it's talking about R and S, and this time air resistance is not negligible, so I have to talk about this. So it makes sense that for R, because it's going to have air resistance acting on it, this is going to be because R has a greater diameter than P and Q, right? So because it's going to have a greater diameter, so there it would face more air resistance. So I'll say that R faces more air resistance because of its greater diameter, right? And then I say, so because air resistance is greater, this causes a lesser resultant force and a smaller acceleration, which increases the time. So the time for R is more. For R. All right. So yeah, that's how you do this one. 8.5, the horizontal component of steel ball Q when it hits the ground is VQ. Horizontal component of the plastic ball when it hits the ground is VS. Explain the difference between VQ and VS. Again, we know that the plastic ball would also face air resistance in the horizontal direction, because air resistance acts the same way independent of whether it's vertical or horizontal. So I'll say that because of this one, for the plastic ball, I know that the horizontal component would be smaller because it would be reduced. For Q, it would be the same, which is because there is no horizontal force. So I'll say that since there is a horizontal deceleration on S, which is greater, and this is basically because of the air resistance, right? Because of its greater size, right? So the steel and the plastic balls, yeah, so which is greater because of air resistance. And you have to explain this. So since there is a horizontal deceleration on S which is greater because of air resistance, Vs is smaller, and this is basically because since the time of fall for Vs is more, S is more, it decelerates more as well, right? So more air resistance as well because of its diameters, but also because we just did this, so time would be more for S, so deceleration also acts more, right? So it falls to a smaller value. Question number 9, the nuclide tritium decays to the nuclide Z by beta negative emission. Complete the decay equation for tritium. So beta negative, we know this is going to be 0 and -1. We know this is an anti-neutrino, and Z we have to balance this. So 0 plus 0 plus x equals 3, so this is 3. And when beta negative decay happens, the proton number increases by 1, and you can see that 2 minus 1 is equal to 1. Line shows the variation with the kinetic energy of the intensity of beta emissions from tritium-3. So you have intensity in some arbitrary units, you have kinetic energy in kilo electron volt, and you are asked to find the speed of a beta minus particle that is at the peak intensity shown in figure 9. Ignore relativistic effects. So first I need to read off the peak. So for the peak, I first just need to see what this read off is. So I think this is what it is, which is, so 2.4 and 2.8, so it's in the middle of that. So this is 2.6 kilo electron volt, which is its kinetic energy. So 2.6 kilo electron volt. So kilo means 10 to the 3, and the conversion of electron volt is simply multiplying by 1.6 into 10 to the negative 19. This is equal to half mv square. So half mass of an electron, you get this from your data sheet, which is 9.11 into 10 to the negative 31 into the square of the speed. So from here you just make the speed the subject, convert, and your answer that you would get is probably something like 3.1 into 10 to the 7 meters per second. Explain how figure 9 gives evidence for the existence of the neutrino. This is kind of an examiner favorite that he asks again and again and again. Why does the alpha decay basically have discrete set of energies, and why do beta have a continuous range of energies? So here it's asking how it gives evidence for the existence of the neutrino. So obviously you know that this is the decay energy is basically shared between beta and the neutrino as well, obviously also between the other nucleus. So the sum of beta energy, or let me say this, so the sum of energies of beta and the antineutrino is constant. Since energy is conserved, and there is a range of kinetic energies for beta, another particle, which is the neutrino in this case. So this is beta negative, right? Yeah, so it's anti-neutrino. So since there is beta negative, another particle must be taking some energy as well. All right, state the minimum and maximum energies of the neutrinos released in the decay of tritium-3. So min and max energies, how do you do this? So the max energy, because it's the sum of both of these, which is constant. So the maximum energy of the beta particle is 18, or it's a bit more than that, right? So it's almost like this, which is like 18 point something, right? So again, we know that it's the sum of both of these is constant. In this case, so this is basically the total energy, right? So if this is the sum of both of these, then the extremes could be this, that either beta takes the 18 point, what seems like 6 kiloelectron volt here, and the other guy then, the neutrino, takes the 18.6 kiloelectron volt, because the sum is to be constant, right? So the minimum energy is obviously going to be almost zero. This is almost zero, it's not actually zero. And the maximum energy is going to be when the beta particles take like no energy here, right? So that is when it takes all of the 18.6 kiloelectron volt, right? So it's shared between the two. So the extremes are when the neutrino takes 0, this means that the beta takes 18.6. When the neutrinos take 18.6, that means the beta takes 0. All right, let's go on to section B now. So figure 10 shows apparatus used to determine the mass m of a ruler. The ruler is supported by a cotton loop that acts as a pivot. A known mass m is hung from one end of the ruler. Position of the ruler is adjusted until it is horizontal and in equilibrium. Horizontal distance between m and pivot is s. Distance from end of the ruler to its center of mass is d. Show that the relationship between m and s is given by this equation. All right. So in this case, this cotton loop is basically the pivot, and I can see that that's this thing then. Okay, so the ruler is uniform, right? It says that somewhere here, yeah. So it's a uniform ruler. So if this is d, then this means that all of this is d as well. So then this distance that we need, this is d minus s, right? So I will say this, that so basically the principle of moments, so mg times d minus s equals m. Okay, so m is a mass, right? And mg is the weight. So I would say is equal to mg times s. Obviously the g's cancel out. I need m as the subject of the equation. That becomes md minus ms over s. So I can write this as md over s minus ms over s. Both of these cancel out. And finally, I can write it like this: m equals to md 1 over s minus m. Table 1 shows values of m and 1 over s. Just a minute. Yeah. So the table shows these values. 11.1 is a plot of m against 1 over s. On figure 11, plot the remaining points from table 1. So 3 are plotted. I have to do the others. All right. So m 0.1, 0.2, 0.3 is done. For 0.4, 1 over s is 6.71. So 6.71. Let's see. So this is going to be 6.2, 6.4, 6.6, and 6.7 is going to be in the middle here. And this is going to be here. Right, let me just place a dot and then mark the cross. Right, it should ideally be finer than that, something like this. And then for 0.5 it's supposed to be 8. This is going to be easy to plot, right? And then for 0.6 it's 9.35. So 9.35, so this is going to be 9.2, 9.4, 9.3, and 9.35 is going to be somewhere here, like this. All right, so that's the plotting of all the points, and then you need to make the line of best fit. All right, let's do that as well. So first I just draw a random line. That's how to do this on the iPad. And then I position this so that's close as possible to most of the points again. So maybe something like this seems pretty nice. All right. So this is ironically one of those things which is easier to do on paper than on an iPad. Determine M. Okay, so M here, if I look at this, this is your y-intercept, right? Because of this, y equals mx plus c. So y-intercept is minus m. Similarly, the gradient is md. So y-intercept is negative m. So negative, this seems like 0.12, 0.14, 0.16. So this is negative 0.16. So m is just equal to 0.16. All right, determine d then. So gradient is md, right? So d is gradient over m. So for the gradient I need 2 points, so let's pick out 2 points. So let's see, probably something like this here. And another point could be this, right? So one of these is 2 comma 0, the other one is 8 comma 0.5. So y2 minus y1, x2 minus x1, this is basically 0.5 minus 0 over 8 minus 2, just 0.5 over 6. That's just the gradient, and then divided this by 0.16. So let's do this. 0.5 divided by 6 divided by 0.16, which is 0.5208. So 0.52 is what I get, right? So that's how you do questions like these. 11, figure 12 shows a stationary climber A of weight 750 Newton on the vertical side of a building. A is supported by a rope and his legs are perpendicular to the building. Section of the rope supporting A is in tension T, makes an angle of 35. A normal contact force acts on A's feet where they touch the building. Weight of the rope is negligible. Section of the rope supporting A has an unstretched length of 1.8 meters. Extension is this much. Young modulus is given and you have to find the diameter of the rope. So the Young modulus formula is E equals TL over A delta L, right? So force, length, area, extension, I need the diameter. So for that I'll need the area, which is TL over E delta L. If you like to, I certainly like to do this, is to do everything first and then plug in the values. So TL over E delta L. So making just d the subject, so that becomes d square equals 4TL over pi E delta L, and then I'll take the square root. So 4 tension was not given. Okay, tension is not given here. So I'll need to find the tension, obviously. So this is 35. So this component is then going to be, because this is 35. So naturally, this is 35. So this one is going to become T cos 35. And this one is going to become T sin 35. So T cos 35 equals mg. So I know this. So first I need to do this. Let's do this here, in fact. So T cos 35 equals mg, which is equal to 750. So T would be 750 over cos 35. 750 divided by cos 35 turns out to be 915.5. And then I plug this in here. So 4 times 915.5, original length is 1.8 pi, Young modulus is 260 mega, mega is 10 to the 6, and delta L, the extension, is 40 millimeters. So into 40 into 10 to the negative 3. This is all d square, so I'll also need to take the square root after all is done. So this becomes 4 into answer into 1.8 over pi into 260 to 10 to the 6 into 40 into 10 to the negative 3. This is 2.017 into 10 to the negative 4. Taking the square root, this turns out to be 0.014, multiplying by 1000 to give this in millimeters. So this is 14.2 mm. So I can write 14. A moves down the rope and then stops lower down the building. His legs are again perpendicular to the building. Magnitudes of T and N are different from their magnitudes when A is in the position shown. State and explain the differences. All right. So he stops lower down the building and his legs are again perpendicular. So in this instance, what becomes is something of this sort. So with him lower down the building, this angle is obviously less. This is the first thing that you had to note. So again, it's going to be equal to the weight, but now if I think about this, because this has gotten smaller, so I can say that cos becomes larger actually, right? Because T cos, I can say T cos theta equals mg. And how the cos function works for acute angles is this, that as your angle decreases, cos theta, this entire thing actually increases, so the tension actually decreases. All right. So as cos theta increases, T decreases, and then similarly for n, I'll say this. So that's T sine theta being equal to n. So for n, what happens is if theta decreases, sine theta also decreases, and t was also decreasing, so n will also decrease. All right. So this is how we explain this. So state and explain the differences. So first of all, you said that the angle of the building and the rope, which is also the angle of the tension with the vertical, decreases since T cos theta equals mg. Right? Since T cos theta equals to mg, as theta uh, decreases, cos theta increases, causing T to decrease. Next for n, so for n what we'll say is this, that since t sine theta equals n, as theta decreases, sine theta also decreases, and since t was also decreasing, n decreases. All right. Figure 13 shows climber B who is climbing up a cliff. B is attached to a safety rope that is not in tension. Bottom end of the safety rope is fixed in place. If B falls, the rope stops her after a short distance. The ropes used in 12 and 13 have the same diameter but are made from different materials. For safety reasons, the rope in 13 has a much lower stiffness than the rope in 12. And again, that makes sense because when we want this guy to stop, we want him to not experience a lot of force, right? And this is linked to ideas of momentum, that since F equals to delta P over delta T, because this is going to be a less stiff rope, what's going to happen is that because it has a lesser spring constant, so it would extend more, right? So if it extends more, then that also increases the time in which he comes to rest, that decreases the force and reduces chances of injury on the climber, right? So this is what I'll talk about now. So since spring constant is spring constant is not what we say in this syllabus. Since stiffness is less, extension is more or is greater by F equals K delta L, which is basically Hooke's law. The tension is also then less. The tension is also, oh no. Okay, so since the extension is more, the time taken to come to rest is more, which reduces the force acting on the climber, reducing chances of injury. Let's now go on to the MCQs. So a tensile force acts on a metal wire of length L, cross-sectional area A. Force causes an extension L, Young modulus is E. What is the stiffness K of the wire? So this you simply get by rearranging the Young modulus formula. So E equals TL over what do you call it? A delta L, right? So tension over delta L, this is basically the spring constant. This is the stiffness, right? So this is KL over A, which is equal to E. So K is EA over L, that is option A. Next, an object of mass m is supported by two non-vertical strings. Magnitudes of the tensions in the strings are T1 and T2. Which statement is correct? All right. So which statement is correct? If these are non-vertical strings, it's probably going to be something like this. This is T1, this is T2, and this is mg, right? So weight is supposed to be vertically downwards. So which statement is correct? So T1 plus T2, obviously this cannot be just equal to mg. That would be the case if they were in the same direction, so if these were upwards, right? But if I do this, then it makes sense that because there are components of both of these tensions that we take here, right? So for example, if this is some theta, if this is some alpha, then I know that it would probably be something like T1 sine theta plus T2 sine alpha equals mg. So obviously there's a sine alpha, there's a sine theta here, and sine and cos of anything is between 0 and 1. So it's actually making this tension smaller and this tension smaller so that they add up to mg. So independently T1 and T2 are greater than mg, that is B. Thrust of a rocket engine has magnitude F and acts in the same direction as the direction of travel. Graph shows the variation of velocity of the rocket with time t. Area under the graph is alpha. Gradient is mu at time t equals to capital T. So at this point, which statement is correct? At t equals to capital T, the acceleration of the rocket is F over alpha. Not true, because alpha is basically displacement, right? So this is wrong. Total increase in the kinetic energy of the rocket is F alpha. That makes sense because this is the work done, which would be equal to the increase in energy. This is true. Average mass of the rocket is F over mu. So mu is acceleration, right? So F over A equals m. But again, this is not true because it's not the average acceleration here. If this was the average acceleration, then this would be the average mass. But rather, this is just the acceleration at this stage. If you did this, that if you assumed this as a straight line, and if you found this acceleration, then that would be the average acceleration, and the force divided by that would be equal to the average mass. But as it stands, this is also wrong. At t equals to t, the power applied to the rocket is F mu. F mu means Fa, which is not anything that we know of, force times acceleration. So that's wrong. An object is projected into the air at time t equals to 0. As shown, it lands when t equals to capital T. Air resistance is negligible. Which graph shows the variation with t of the acceleration A of the object? So the acceleration is a constant which is downwards, which is the acceleration due to gravity. So which one shows constants? It's just this one, which is A, right? 16. Trolley P has mass m and moves with a velocity v on a horizontal surface. P collides with a stationary trolley Q. Q has a mass m. The collision is elastic. What are the velocities of P and Q immediately after the collision? So with elastic collisions, what happens is that the relative speed of approach equals the relative speed of separation, right? So initially, if I have P and that is moving towards Q, which is stationary, so the relative speed of approach is just V. And after the collision as well, it must be the same. If you have both traveling at V by 2, and again, because you have negative signs as well, it means in the same direction. So there is no relative speed of separation. Relative speed of separation is 0, which is not possible here. Similarly, it's also 0 in this case. And in this case, this is negative V. So this goes like this. And 0, basically, Q does not move. Now, if you think about this, in this case, the relative speed of approach is V, relative speed of separation is also V. But this violates the conservation of momentum, because if the total momentum before was to the right, then the total momentum after must also be to the right. So this is wrong, and this is actually what fits our descriptions. So this now comes to rest, and this travels with the speed V after the collision. A radioactive nuclide X emits alpha particles. Energy from the alpha particles is used to power a device. Each alpha particle has a initial kinetic energy of this much. Device requires an input power of this much. What is the minimum number of nuclei that must decay every second, right? Okay, so this is the power, 0.2 milliwatts. This is 5.9 mega electron watt. So mega electron watt. So 1.6 into 10 to the negative 19 is what it is usually, just the electron watt, electron volt. So then you multiply by mega, which makes it 10 to the negative 13. So that gives you the number of nuclei required. So you just figure out what this fraction is equal to. 5.9 into 10 to the negative 13 into 1.6. So this turns out to be 2.118 into 10 to the 8. So that is B. An electron is accelerated from rest by a constant force F over a distance of 8.5 centimeters. Final velocity is 6.2 into 10 to the 6. What is the magnitude of F? So I have the final velocity. So I basically know the kinetic energy then. So half mass is 9.11 into 10 to the negative 31, and speed is 6.2 into 10 to the 6 squared. So the increase in kinetic energy must have come from the work done. So F times 8.5 centimeters, that's 0.085 meters. And from here you just calculate this. So half into 9.11 into 10 to the negative 31 into 6.2 into 10 to the 6 squared. Divide this by 0.085, and this turns out to be 2.0 into 10 to the negative 16. So 2.1 is then the closest one. This is the answer here. A light spring is placed on the floor and is in equilibrium. A ball of mass 130 gram is placed on the top of the spring, causing the spring to compress by a distance delta L. A force F is then applied so that the spring compression increases to 4 delta L. And I know that if it's obeying Hooke's law, so for 4 times the compression, just as how it would be for 4 times the just as it would be for 4 times the extension, the force must also be 4 times as much. And then it says F is removed, causing the ball to move vertically through a distance h. The spring has a spring constant of 58 Newton per meter and obeys Hooke's law. What is the maximum value of h? All right. So for the max value of h, we'd say that in this case, it's basically, so this is the max value of h is how far up the ball goes, right? So I'd say that in this case, I have the spring constant, which is 58. So half kx square, that basically becomes mgh in this case. So I know half spring constant is 58. Extension or the compression in this case, when it's pushed all the way down, so that's 4 delta L, right? So x is basically delta L. So that's 4 delta L squared, but I don't know delta L, right? Okay, but I do know this. So I know that when the mass of 130 grams is placed, the distance is delta L, so I can figure out the extension. So if I use this, so F is mg, so 130 over 1000 times 9.81. This is equal to k, which is 58 times delta L. So I can figure out delta L like this. So 130 divided by 1000 into 9.81 divided by 58. So delta L is 0.0219 meters, right? And this is 4 delta L. So this is 4 times this. Again, let me write this as delta L to avoid confusions. So this is going to be 4 times that. Times 4 is 0.08795 squared equals mgh. So m is 130 grams, so 0.13 times 9.81 times h. So half into 58 into this answer, squared. Answer divided by 0.13 times 9.81. So ACE turns out to be 0.175, which is C, 0.18 meters. So this was a really challenging MCQ as well. Which stress strain curve shows the greatest work done per unit volume? So work done per unit volume is the area under a stress strain curve, which looks like the most for B, right? So it's going to be B in this case. So that has like the most boxes underneath. 21. A student measures the diameter and mass of a solid metal ball. He uses the values to calculate the density of the metal. Student quotes the density as this much. Uncertainty in the measurement of the diameter is this much. What is the uncertainty in the measurement of the mass? Also a good question. Since density is mass over volume, and volume I would calculate as the diameter, that would be 4 by 3 pi r cubed. So that would be m over 4 by 3 pi r cube. So what I end up concluding is the density of the percentage uncertainty in density is percentage uncertainty in m plus thrice the percentage uncertainty in either the radius or the diameter. Whatever I say doesn't make a difference. So here I have these, so I can find out the percentage uncertainty. 120 over 8,000 times 100. This is 1.5% uncertainty here. The mass has a uncertainty that we don't know, right? We need to find this, and thrice of this much. So this is 1.5 minus 1.2, which is 0.3. So these are all technical questions. Radius RA of a gold nucleus is approximately 140 picometers. The radius Rn of the gold nucleus is approximately 7 femtometers, and you need the ratio of Ra over Rn. So Ra 140 pico is 10 to the negative 12, and 7, this is femtometers, it is 10 to the negative 15. So when you do this, this turns out to be C. Which pair of particles can be produced in a single pair production event that produces a particle and its antiparticle? So electron and protons are not antiparticles. They are not antiparticles. This is antiparticles. This is not antiparticles. A radioactive source emits beta, negative, and gamma rays only, so no alpha. Corrected count rate from the source is measured over a long period of time. Four different sets of absorbers are placed between the source and the detector. Corrected count rate is measured for each set of absorbers. Set of absorbers are a 10 centimeters air gap only. So, and then a 10 centimeter air gap and a 4 millimeter thick aluminum sheet, which would basically block out beta, right? So with the 10 centimeter air gap, there should be no change to the count rate, right? And then with the beta, with the 10 centimeters, so it must drop. And then the 20 centimeter air gap only, right? Okay, so in this one, what you end up seeing is this. So you know that through the air gap, there is going to be both beta and gamma. But after this, after the aluminum sheet, the beta gets blocked out. So what remains is gamma. And then similarly, you have the 20 cm air gap only, and then you have the 20 cm air gap and aluminum sheet. Again, after this, you know, this is only gamma left. So this is only gamma, this is only gamma. So now when we think about this, so we know that for gamma, there is the inverse square law. Now, if I think about this one, I know that this is 10 centimeters, and I know that this is the count rate, which is the same for all of these, which is 300. So I know that since the count rate is proportional to 1 over r square, so I can say that is equal to k over r square. So CR square equals to k, which is going to be 300 into 10 square, right? This is the value of the constant, which is 300 and 2 more zeros, right? This is 30,000. So when I want to find out what the radiation is here, I know that because the distance has doubled, the count rate is supposed to be a quarter of what it is. So for that I can use the equation again, since C equals to K over R square. So this time it's going to be 30,000 over R square, which is 20 square, and this turns out to be 75, right? So it's actually this column here, which is option D. So this was also a very technical question. Nuclide 232 decays to nuclide this by a series of alpha and beta decays. How many beta negative decays are there in the decay chain? So just by figuring out the difference in nucleon number, I can find out how many alpha decays there were. So basically each alpha decays causes the nucleon number to decrease by 4. So 232 minus 208, this is 24. So 24 over 4 means this is 6 alpha decays, right? So when alpha decays 6 times, so this must also then decrease by 6 times 2, because each alpha decay is a helium nucleus, that's 2 protons. So this must have decreased by 6 times 2, which is 12. So that is 78. But if this is 82, so this means it has increased by 4 more, and that would have become because of each beta decay, which is A. So there are 4 beta negative decays as well. So that wraps up this paper for IAS physics. Let me know if you guys have any suggestions. Like, share, and subscribe to the channel, because there will be much more good stuff like this coming your way to help you with your exams. See you later.